Okay. Okay. Well, I think people will keep joining us. I think we can start. There are people already with us on YouTube. Nina, I'll do a short introduction and then I will pass you the floor, okay? So let's start. Hello, everyone, and welcome to another talk in our webinar series. Today, we have the pleasure of having Dr. Nina Hernitschek from the Vanderbilt University. She's an astronomer very interested and involved with big data challenges in astronomy. And she's been working with computational efficient machine learning solutions, data stream processing, and real-time data processing, to name a few. And she also works studying the dynamical history of our Milky Way. Today, she has joined us to talk about the Lsst Community Brokers, especially an overview about the point of interest broker developed by a team at Vanderbilt University. Before we start, a quick reminder, this webinar is also being streamed live on YouTube. You can find the link on our website, or you can access it on our YouTube channel, LIneA MCTI. Nina, thank you very much for being with us today. The floor is yours.
Thank you very much for inviting me. So today I will first give a brief introduction in Lsst, its alert processing and distribution pipeline, the broker system, and then finally in a point of interest broker, which is right now developed at Vanderbilt University and serves very specific purposes towards variable star science. So the Lsst survey, to give a brief overview, will have an 8.4 meter telescope, 6.7 meter equivalent. It is equipped with the world's largest CCD camera, and it's observing in 6 optical bands. So we are covering from the U to the Y band, which is somewhat rare. So most surveys only have 5 bands and specific use cases. So for example, quasars require observations in the U band, others require observations in the Y band. So it's very good that Lsst is covering such a wide range in the optical. The field of view of Lsst is quite large. You see it here in this image, a comparison between the field of view of different, nowadays rather large surveys. So Lsst is somewhat in the middle between PS1 and ZTF, but differently than ZTF, it has a wider waveband coverage, and it will also observe deeper. The survey will be conducted for a 10-year baseline, and Lsst will take about 1,000 images per night, and this sums up to about 15 terabyte of data volume per night, with about 10 million detected transients per night. Lsst is expected to have its first light from the ComCam in October 2022, and about a year later, it should finally start its operations. So we're hoping that everything is going within this timeline, because it was a bit postponed, of course, but we're really hoping that it will be available in 2 years. The number of visits differ widely over the observed sky. This is because Lsst is composed of different sub-surveys, whereas the so-called wide, fast, deep survey is the largest, with the most number of visits, or the second most number of visits, or a small parts of the survey called the deep drilling fields that are going deeper and having more observations. And within the main survey, in the wide, fast, deep survey, the sky is observed 2 times per night, every 3 nights over 18,000 square degrees. The distribution of the individual pointings is calculated rather on the fly by a machine learning algorithm. So there is no predefined pattern on how the pointings are carried out, but it is decided based on weather, on special observing programs, on the moon phase and things like that. This is a rather new concept. It's one of the many things where LSST comes up with new concepts in contrast to large all-sky surveys we had before. Science that can be carried out with LSST is expected to be of a very, very broad range. So it was defined to specifically serve 4 science areas, sometimes also called science pillars, which are going from cosmology down to solar system physics. So one of them is probing dark matter, dark energy. Here, LSST will be very helpful as it's a very deep survey and it's covering a huge range of the sky, and it has a quite good cadence so that we can pick up objects with a good and a long baseline Likert. Then it will be also used for cataloging the solar system, so finding and following asteroids. Here also it's very good cadence is extremely helpful, as well as the cadence will what clearly will also benefit from the good cadence is variable and transient astrophysics. So what is specifically important for this is having very good sampled light curves that are, as far as possible, covering a huge waveband range, as well as having a rather long temporal baseline. So many of the more traditional surveys suffer from either being focused on a quite small part on the sky, or having a target input list, or they scan or sky like PS13Pi did, but they suffer a lot from the cadence. So I was working a lot with PS13Pi survey, and at first it looked really nice having a wide footprint, a somewhat deep survey, but then when trying to do variable science with that, it becomes very, very difficult, for example, to measure the periods of variable stars, as the cadence was just not made for that. And with LSST, it will become much better. This finally will help us also to map the Milky Way by using, for example, variable stars. So overall, LSST will be a deep, wide, fast, and long baseline survey. And so a lot of science will just benefit from that. LSST will generate so-called data products. This is data that will be available to users in the astronomy community, but it will also be available to the public quite early on. What is going on in the processing pipeline is after readout, we will have immediately raw data, and just 37 seconds later, so-called prompt data products are calculated from different image analysis. And this is where the alerts are generated, which will then serve the brokers. I will talk a lot more about this later on, but just as an overview, that we have multiple steps of LSST data products. Those results from the different image analysis, then go into so-called prompt products database with images, objects, and a source catalog, also covering solar system bodies. And each year, an annual data release will come out via the LSST science platform and data access centers. And when all of that is done after 10 years, there will be, of course, a final 10-year data release. And I mentioned this here especially also to highlight the sheer data volume. So we're having about 20 terabytes per night of raw data. We have about 10 million individual alerts from transient and variable sources per night. And the total data volume will cover about 15 petabytes. So this is so large that traditional approaches with downloading data and processing them locally on a data center or on a cluster or even on your laptop, they won't be feasible anymore. So LSST has to rely heavily on data products, on processing, and on redistribution pipelines. What is very, very important here is that astronomy is largely determined by the availability of computational capacity. And we should work as hard as possible to not be limited by that. So we have a lot of observations coming in from LSST, but it would not be feasible to do more complex data evaluation methods on the vast majority of those data. So telescopes and instruments in this view are more seen as front ends for data processing systems and follow-up telescopes. So what is coming in from the data, it needs to be carefully processed in pipelines that are usually requiring multiple steps to select sources, to do a real bogus discrimination, and so on. The challenge as well as the chance here is understanding complex phenomena in astrophysics requires complex data. And it sometimes requires a lot of data. For example, when we want to do so-called population studies, we're observing a huge population of stars which are from the same type, and we want to know, for example, are there specific subtypes or are there certain connections in a perimeter space? Typical use cases that can arise from such complex data are, for example, hunting for unknown unknowns. This means objects that have a specific unknown behavior that we even have never thought about. So we're really not knowing that something like that could exist in the data. So we're not knowing what we're looking for, but it could be there. And it is quite sure that in this mass of data, there will be unknown unknowns. Then another use case is known rare 1 in a million events, something that we know from theory, but that we have never observed, or maybe once or twice observed, and we cannot not really say anything about this right now because we have just too few samples. Then there are, for example, objects that require an immediate follow-up. This is the case, of course, for supernova, for merger events, which trigger then multi-messenger observations. And there are also some objects that are requiring follow-up, but not that immediate. But it's more important to have accurate and up-to-date light curve information, as those objects change. And we have to know how bright it is at a certain time. We have to predict its brightness because we can then make some assumptions about the ongoing physics behind that. I will also talk a bit more about this later on, as we have such specific use cases where this is the case where we need to predict light curves. So this is what will be just possible with LSST, because it has a large footprint and a high cadence. So it allows for detailed light curve analysis on its cadence and a long baseline, as well as for statistics from a large data set where it will heavily benefit from the large LSST footprint. And we need software systems that are able to sort and filter alerts after they're produced by the pipeline at a scale to enable better follow-up. To come back again to this picture, here, those alerts that are generated within 37 seconds are exactly what are triggering the alert brokers. And how are those alerts created? So what is going on behind the scene is there is a real-time difference image analysis processing going on in the pipeline, and this then creates a stream of alerts which is containing data about individual transient, variable, and moving sources. The alerts will then be distributed to brokers, which are software systems specifically designed to ingest, store, process, annotate, redistribute astronomical alerts to a broader scientific community. The typical functionality that we can expect from such systems is to cross-match with archival catalogs. This will help with identifying objects. So we can say a lot, but of course not all objects that are observed or will be observed by LSST have already been observed by other surveys and or in catalogs, but we just don't have such good Likers from them, or they can be associated with an object. For example, there's a supernova that of course was known before, but maybe we have known the star, or maybe we have at least known the galaxy in which it's happening. Then another functionality is photometric classification based on the light curve analysis. This is necessary as a lot of objects that are already cataloged have wrong types assigned. This is just because other surveys quite often had not the photometric cadence and depth to make a classification straightforward and clear seeing. So for some tests, I looked through objects from the variable star catalog VS6, and we found that depending on the type, about 5 to 10 of those objects are clearly misclassified right now. And here, a classification pipeline that is then based on better Likers from LSST will help to resolve these misclassifications. Another typical functionality that should be available from brokers is the identification and the prioritization of objects that are possible for follow-up observations. So to make just an example, from the photometric classification, we might see that a certain star is indeed an Lyris star, but it's not a Cepheid like it was maybe cataloged in the VS6. And then an observer might get a notification from a broker that this object was again observed. And now we have an updated light curve, and we now know its specific phase at a specific time. And so this observer can do a successful spectral or spectrophotometric follow-up. I will also talk a bit more about this later on, because this is exactly our use case. And then, of course, the broker should allow an easy user interaction. So by providing user interface over a web service, by allowing users to download specific data. Just as I mentioned before, we cannot download everything, but we have to channel the data and have to enable the user to specifically download what they need for their use case. So those brokers are usually covering rather wide range of functionality, but all of those brokers are somewhat different. especially in their focus on science use cases. The broker were selected in the following way. So there's an anticipated very, very high bandwidth from Rubin Observatory alert stream. And this then limits the numbers of brokers that can really receive the stream directly. All this started in May 2019 with letters of intent submitted by 15 developer teams. Then there was a community broker workshop held. There were many follow-up workshops in this direction. And then finally, in August 2019, full proposals were submitted from 9 broker teams, and all of them were selected. There were 7 of them are full stream alert brokers, which get directly the stream from the LSST and will serve a rather broad range of science use cases, and will then also forward their stream to so-called downstream alert brokers. There are 2 of them, and I'm working on a point of interest broker, which will get its stream from Enteris. I will also talk a bit more about how this specifically works later on, but this here just as an overview on how the broker systems interact with each other and how they're interacting with Rubin Observatory. What's happening specifically at Rubin Observatory is the alert production. This means, as I said briefly before, it's processing new data from the telescope with a difference imaging analysis, and with a signal to noise ratio larger than 5, it's assumed that a source is detected and a record is written to source catalogs, and an alert is generated. An alert is a package in Avro format, currently distributed over Kafka system, which is containing coordinates of sources, photometry, which is the recent observation and a bit of a look back, image cutouts from the science images, and then other information, which could be, for example, light curve features, which are calculated properties of a light curve, something like amplitudes, periods, and other information. These alerts are then distributed by using an alert distribution pipeline. Here is a short overview of this. The time average data rate of the alert stream is estimated to be about 0.2 gigabytes a second, and voice bursts up to 5.4 gigabytes a second. So it can vary somewhat. The estimated size of the alert database after 10 years, about 2.2 petabyte. This is also something that's a bit a problem for the broker system. So they have to make sure they can store all this information, because the brokers should store the alerts and not only process something, forward it, and then the information is gone. So this alert distribution pipeline is directly serving the brokers with it's generated alerts in Avro format over Kafka. Quite often the question arises how we are testing those systems, as LSST isn't available yet. So there are some pre-LSST alert streams that are working just the same way, but a bit of smaller scale. Currently, the broker systems are tested with ZDF alert streams and an archive of ZDF alerts made available by the University of Washington. So this archive will exactly do what also the brokers will do. It will store the alerts to have them available later on, and the stream is always containing the alerts from the night before, and then the stream is emptied. To compare ZDF with LSST, we see that LSST is of course much larger. For example, it's about 7 times the number of detections. It's about 37 times the number of objects. The nightly alert rate is about 10 times that of ZTF. This gives about an idea on how much we have to scale up the systems that are working just right with ZTF. The anticipated content of an LSST alert stream will be similar to that coming from ZTF, but it will also differ a bit. So what will be the same is it will contain cutout images. It will contain photometry and a lack of history, but the history from LSST will be looking a bit back further than from ZTF, where it's only 30 days. Then LSST will have an improved machine learned real bogus score, and it will also come with a huge set of calculated Likert features. Right now, brokers have to calculate their own Likert features, something like periods, amplitudes, steepness, and things like that. But a lot of that is expected to come then directly from LSST. And different brokers will have different capabilities. And as I said, they were directed towards different science cases. I will now specifically focus on the point of interest broker, which is a lightweight broker for variable store identification, classification, and follow-up. Before really going into the technical specifications, I will first talk a bit more about the specific use case that led us to the idea of developing such a broker. So the background of all of this was a project to characterize the Milky Way from variable stars. Of interest are specifically are Lowry stars and Cepheids. They are easy to detect, or somewhat easy to detect, and they stand out because they have a specific Likert profile, like it's shown in this image here. And they are a very valuable resource because they allow for a distance measurement from the period luminosity relationship. So when we detect a lot of those stars, we can build a 3D model of a Milky Way, because then we can add accurate distances. And this will help us in the detection of structure, substructure in the Milky Way, such as tidal streams and dwarf galaxies, which will help in answering questions regarding the formation and merger history of our Milky Way. What you see in the following image, is one example of such, how we call it, a point or a region of interest. So there are dwarf galaxies, globular clusters, and there are stellar streams. And this here is the Sagittarius stream, with a study from PS1 3Pi and our Lowry stars, which we selected from the survey. We were able to get the first complete 360-degree view of the Sagittarius stream. This helped us in building a model of the stream and also in identifying substructure within the stream that was not known before, because our surveys just were not deep enough to cover all of the Sagittarius stream, and other surveys or the processing pipelines also lack the capability of accurately identify and classify variable sources. So this was possible with a machine learning technique that was capable of selecting stars from the rather spare PS1 3Pi survey and clearly identify our Lowry stars and accurately calculating their periods and phase to then calculate the distance. What we're also interested in is variable star follow-up. Follow-up here means specifically spectroscopic follow-up, because when we have the added information from the spectra, we also know the 3D velocities. Usually from something like Gaia, we only have, or we are only able to calculate the on-sky velocities from the proper motions, but what we also want to know is the 3D velocity to then identify true co-moving groups and clusters in the Milky Way. And for this, we need very, very accurate Likert information, because the trick in this is doing the spectroscopic observation just at the right phase of the variable star. This is important because the cause of the pulsation in the star is also causing a change in its brightness. So when the star is shrinking, the surface is heating up, and then when it expands, it cools again. And this is what we see as a change in brightness, and finally leads to this very well-known Likert shape. This then enables us to exactly calculate when the star is neither expanding nor shrinking. And this is happening at a phase of 0.37, which we have from theoretical models. When we can calculate the accurate Likert shape, the accurate periods and phase offsets, then we know specific times for observing when phase 0.37 is happening. This was extremely tricky for us because we had at this time only data from PS1 3Pi, where the data quality in some cases was good enough to do that. In some cases, it was not. In those cases, we later on relied on data from ZTF, which has a much more better sampling. This then led to an observing program with a collaboration of Caltech and Carnegie observatories starting some years ago in spring 2017. And the overall goal of this project was to dynamically characterize substructure in the outer galactic halo by using Keck and Magellan spectra with the timing we got from PS1 3Pi and from ZTF. So this was some of a background, which finally led us to the idea, how can we make this easier? Because as I said, we had a lot of trouble in getting the right data. And then we thought about what can we do with LSST when it becomes available. It would be extremely helpful if LSST had something that enables users to say, this star was observed again. We have now a calculated light curve, and this specific phase is happening at this, and this observing times, and then the user can pick an observing time to do their spectroscopic observations and can do observing planning. So this was basically the idea behind the broker, enabling follow-up for variable star science. And this is specifically interesting because first we can do a detailed analysis based on a high light curve cadence, and then we can do statistics over large samples based on survey footprint and duration. Because in this variable star science, we're always looking for larger samples to test certain assumptions, or to look for specific objects that are behaving differently. And for example, we're also interested in knowing more about how large is a fraction of variable stars which are showing an amplitude and phase modulation. So this is only possible when we have a lot of data and we have so detailed light curve information that we can do light curve evaluation and phasing just from subsequential short baselines. So we can see if the period or if the phase offset is changing over time. And the alert broker to enable users to get this and get updates on variable star observations within specifically interesting regions. The idea then evolved that we want to enable users to access predefined and user-created interesting regions. Predefined is very important because variable stars are mostly found in stellar streams, dwarf galaxies, globular clusters. So we can expect that users are interested in watching them, and also user-created interesting regions, like we saw from our research on the Sagittarius stream, where we detected some substructure, and maybe a user just wants to follow up just that. To look back about to the science goals of Lsst, this will specifically add value to 2 of the 4 science pillars as specified by Lsst. One of them is exploring the transient optical sky, and the other one is mapping the Milky Way by using a large and deep set of variable stars. PS13Pi, as we saw, is clearly pushed to its limits, and of course we want to make use of the upcoming Lsst, as it will be at least 2 magnitudes deeper, and so finally enable us to see more of the outer halo, where, as you see in this picture, PS13Pi was just able to look about out into most of the outer halo, but it became fuzzy towards the outskirts of the outer halo. We often had then Likert with just 10 data points over 3 or over 5 years, and you cannot really do variable star science with that. Data products and services available by the point of interest broker then will be, for example, Likert, co-added Likert of all LIneA and Cepheid, stars in specific regions, and value-added information such as period, phase offsets, also modulations of period, amplitude, phase. And this is specifically tailored towards astronomers who want to do follow-up and who want to calculate distances. Here you see an image of what I briefly mentioned regarding modulation of Likert properties. This is a Likert from Kepler, and it shows very, very clearly how the amplitude is modulated, and how the change in amplitude is modulated for this specific all-LIneA star. This is, of course, a Kepler Likert, so it has a rather short baseline, but from Lsst, we can observe this over a much longer baseline, so we can see what is really going on with the amplitude or with the phase modulation in such stars. What you also want to do is doing cross matches to provide information on variable stars within defined regions. Alert broker thus should perform a cross match with variable star catalogs, such as here the PS13Pi sample catalog that I created and used in further studies on the Milky Way history. And this should be available as soon as Lsst gets operational, because we just need to cross-match positions and magnitudes, and then classification of variable Likerts. This will be happening as soon as a Likert quality is sufficient for doing that. And also what we anticipate is doing catalog cleaning, in which catalogs that are already existing or the stars that are cross-matched are processed again, and then we're comparing the outcome of the classification process. As we had seen, for example, with VS6, there's about a 5 to 10% contamination rate currently, which clearly comes from the fact that it was mostly built on Likerts that just cadence and characterizing and classifying those sources. The user access of the point of interest was defined to be quite simple and straightforward. Simple user interface, data query language for advanced tasks. Tables can be looked up with the web interface, but can also be, of course, downloaded where you can see overview tables of objects observed in a specific region. You can filter regarding Likert features and so on. I will show screenshots of the web interface in a moment. So it is composed of a broker backend, which has the functionality I briefly mentioned before as a broker functionality to ingest and store stream content, doing Likert generation, currently with ZTF to concatenate a Likert beyond the 30-day limit that is provided within the alert, which has a short look back Likert. Then the broker backend of the point of interest broker is also annotating the stream by doing feature calculation. And it is doing cross match by using the CDS match service with, for example, Simbad, Allwise, 2Mass, Pen stars, then our specific PS1 3Pi or Lyric catalog, and many others. So it's currently cross-matching to about 30 catalogs. And it's also comparing the outcome of the cross-match. This is implemented in Python with C++, which is connected with Weave. And we're currently storing the data in a simple SQLite 3 database, but we can, of course, also exchange this with another database. We're currently using this to process the ZDF alert stream and also to process the archive. The broker front end has a functionality of serving as a user interface over a web service, of allowing to select and filter alerts, displaying science images, calculated features and cross matches, and allowing for download data. This is implemented in Python with Flask and SQL Alchemy. Here you see a few screenshots of the broker system, which we're currently testing, and also we're doing some changes. I will say a bit more about this later on. So when the website is opened, it's basically just displaying a list of the latest alerts, where it is displaying some basic information, which also can be filtered, like date, candidate ID, observe filters, position. You can do a region search, and it's also giving information on the magnitude. Then when clicking on a specific object, you first see a Likert overview, which is showing the concatenated Likert as well as the science image cutouts. And it is showing a long list of calculated features, as well as it's showing a classification, or let's say better here, cross-match, where the object is cross-matched to a lot of different astronomical databases. We will also include cutout images from that. What is currently happening is that the point of interest broker is now becoming a downstream broker from Antares. So we will reuse the alerts, the concatenated Likerts, also some annotations like cross matches and features from Antares, and whenever possible also their classification. And this allows us to more specifically focus on very specific classification like amplitude, phase, period modulations, also watching for such modulations happening. Also, we are maintaining a list of specific points of interest coming from recent publications and also user created, and we're doing specific calculations for follow-up observations, which means calculating phase and time from Likert models to serve observers with specific times on which they can do their spectroscopic follow-up. So that's it for from the point of interest broker. And now I'm happy to answer any questions that might come up. Thank you.
Thank you. Wait a moment. Okay. Thank you very much, Nino, for the very interesting talk. Now we have time for questions from the audience. If you joined us on YouTube, you can post your question in the comment section. And if you joined us on Zoom, you can raise your hand and ask it yourself. So questions? Okay, while we wait for questions, I have some questions. Okay, Julio has a question.
Please go
Julio,
ahead.
go ahead.
Okay. So, hi Nina, thanks for the hi. It's excellent presentation. I have one doubt about the. I don't think I completely understood the role of the downstream brokers. They will be more. They will have their focus on specific science or specific kinds of alerts, or I don't know. They will process everything, but just a subset from the mainstreams.
The downstream brokers have the specific purpose of getting only subset of the alerts because they're serving very specific user science cases. So okay. For example, as we are working with variable stars, we don't want to get the alerts which are, for example, associated with asteroids or so, because otherwise we would have to filter them out. But an upstream broker, just like Antares, can do that for us, because they are doing feature calculation and classification. And when, for example, a specific object is an asteroid or a non-variable star, it will just not be included in the stream that we will get. So this helps the downstream brokers to focus more on very specific use cases, which also might require a bit more computation time.
Okay, clear now, thanks.
Thank you, Julio. More questions? Julio, you have another question? I think you raise your hand again. Or?
Oh, I just, oh, sorry.
Okay.
Okay, no, sorry.
Okay. No problem. I have a question about, you told us right in the beginning that there was this cut on signal to noise ratio, signal to noise ratio bigger than 5 to get the alerts. Does this happens at the LSST, or is this on? Could you revisit the explanation, because I think I didn't understand.
So from the DAA pipeline, if the signal to noise ratio is exceeding 5, then this is assumed to be a detection, and then it will be included in the stream that is then forwarded to the brokers.
Okay, thank you. Well, I will continue with my questions while we wait if there are more questions. You will the point of interest will focus on variable stars. You are interested in periods and phases and to characterize your stars. There is a type of star that maybe isn't. I don't think you will study this type of stars, but the B stars, active B stars, BE stars, when they get active, eject matter, they are the photometry, it suddenly goes higher. So do you have any ideas of maybe what broker will analyze, of do you have any plans of including other types of target stars?
We're currently looking through the list of variable star classifications that Antares can provide. And then we need to explore what we can specifically do with different types of other variable stars. So right now it's more focusing on the pulsator type. So our Lyrae stars Cepheids, where you have a somewhat sinusoidal-like curve shape that can be undergo some modulation or not, and where you can calculate over some baseline when it's just the right time to do a spectroscopic observation. So the use case would be somewhat different, but we expect to include more variable stars, and these stars would be a really good candidate for that.
Yeah, that's nice. And if someone, let's say someone here in Brazil is interested in this point of interest, will it be open? Does one need to subscribe? How is the process, or is it closed?
It will not be closed. So right now it's not publicly available, but it will become shortly after we switch to getting the downstream alerts from Antares, and then we will make it public, and then everybody who's interested can just use the service.
Okay, that's nice. More questions? Well, I will ask my last question, I promise. You told us that, at least I understand in this way, that those variable stars, they are easier to see in stellar streams. Why is that? I didn't get it. Got it.
So this is just because they have a known Likert pattern. And so for classification, one can use something like, for example, template fitting. So one can write machine learning code that is specifically looking in the data for this specific known Likert shape. When something about like that is happening, it leads to classification over multiple steps. So to go back to the PS1 3Pi survey, where we had rather sparse Likerts. What we did as a first step to go through this huge amount of data was to calculate statistical properties of Likerts, which are called structure functions, which give not a precise period, but they give a baseline for temporal variation, and they give something that is related to an amplitude. This then gives a pre-classification, and then in a second step of classification, we can use a template of our Lowry stars to specifically compare the light curves to that template, and then to do phase folding to find the correct period. So this benefits usually from the fact that our Lowry stars, as well as Cepheids, have a very well-known Likert behavior, in opposite to other stars where we have, like in B-type stars, where we have sunbursts or some chaotic behavior, where it's much more complicated to build a model, and where we need much more precise data in order to find them.
Okay, but maybe I wasn't very clear. But does it has a correlation of being in stellar streams, these stars? Like if I wanted, that was maybe I misunderstood.
Okay, I know what you mean. So it's like that. Our Lowry stars are very old stars, and we assume that globular clusters, dwarf galaxies, are also a very old substructure of the Milky Way.
Okay.
And so they're very good, they're ideal tracers of this substructure. And then when you assume you have a globular cluster which is stretched out into a stellar stream, then the stream becomes rather thin. And then in front of the background of all the Milky Way stars, how do you make out which is the old content? Yeah, you can, and which is a stream. You can do this by looking for the Larry stars, which were already present in the stream when it was a globular cluster.
Okay, now it makes sense. Now I got it. Thank you. Thank you very much. Well, I think we have time for our last question. I apologize for taking all the time. Okay. All right, so if there are no more questions, we will now wrap this up. This presentation will be available on our website and on LIneA's YouTube channel. And for the next week's webinar, we will have Andreu Font Ribeira from the Universitat de Barcelona, continuing in our series on the dark energy spectroscopic instrument. Well, thank you everyone for attending, and a special thanks to Nina. Thank you, Nina.
Thank you for inviting me. Thank you.
Thank you very much. Everyone, have a great day, stay safe, and I hope to see you all again next week. Thank you. Bye-bye.
Thank you. Bye-bye.